So we spent a lot of time in calculus talking about tangent things, tangent lines to curves, tangent lines to functions in BC calculus. And so it may come as no surprise to you to ask, well, can we make a tangent plane to a surface? And the answer is, well, yeah, absolutely we can. So here we've got some function, and we'll call this function, this is z equals f of xy. And we're going to try to find the tangent plane at a specific point, x0, y0, z0, where, z0 equals, hopefully this is clear, f of x0 and y0. So if we look around that point, obviously we know just from our examination of planes that our plane needs to look something like this. Some number, x minus x0, some other number, y minus y0, some third number, z minus z0, and that's going to be equal to 0. I'm going to rearrange this a little bit and divide away by this constant, big C here, just to write it in a slightly different way. So I'm going to write it as, rewrite it this way, z minus z0 equals little a, x minus x0 plus little b, y minus y0. And if you're curious what's happened here, little a is negative big A over C. Little b is negative big B over C. We don't actually need to worry too much about that. I'm just rearranging my my thing a little bit. And so this is almost the equation of a plane. We've got x0, y0, z0. The question is, what do A and B represent? What do little a and little b represent? So let's start by looking at little a. Let's imagine now we kind of look at this tangent plane and we say, well, what happens if we hold y constant and we only move in the x direction? Well, if we hold y constant around this point, as in if we hold y equal y0, and we move along that kind of plane, y equals y0, well, obviously y minus y0 becomes 0, and so our plane kind of looks like this. Z minus z0 equals a, x minus x0. So a is the slope then of what happens to z when we change x. Because if I change x, I multiply that by a and I get some response in z. Well, we already know what a slope is. This is the slope if I hold y constant but let x change. Well, we know what that is. That's our x partial derivative. And similarly, b is going to be our y partial derivative. So we can actually write a very important little equation here. We can actually rewrite this way. We can write our tangent plane as z minus z0 equal to f of x, or fx, excuse me, the x derivative. Now, I just want to be clear here. We actually need to evaluate that derivative. So this is the value of that derivative at the point x0, y0. X minus x0 plus fy evaluated at that same point. Y minus y0. And I'm actually going to give a big old circle around this because this is the equation of our tangent plane. This is the equation of our tangent plane. So here we've got the x derivative and the y derivative in here. And I cannot highlight enough that we have to evaluate the derivatives at that point. We are figuring out what the derivatives fx and fy are at the indicated point x0, y0, not just in general. We want a specific number. So let's try this. And we're going to do a little example over here on the side. So we're going to take our good old Pringle. We're going to take f of xy equals x squared minus y squared, our hyperbolic paraboloid. And I want to find the tangent plane at the point x equals 2, y equals 1, z equals 3, at the point 2, 1, 3. All right, well, first I've got to take some derivatives. So I'm going to go ahead and do fx here is 2x. But again, I have to evaluate my derivative. 2x is what my x derivative is at any value of x, but I want it specifically at the point where x equals 2. So that means that my x derivative is positive 4. My y derivative here would be negative 2y. So again, evaluating that at the point 2, 1, I get negative 2. So at this point, 2, 1, 3, if I increase x, my function increases. If I increase y, my function decreases. And so now I can put this all together, and I can get make my plane z minus 3 equals 4 x minus 2 minus 2 y minus 1. And if I rewrite this whole thing, if I just kind of multiply everything out, I get the plane 4x minus 2y minus z equals 3. And it's worth noting here, there's our tangent plane. It doesn't either way you like it. There is our tangent plane. And if I plug in the point 2, 1, 3, right, I get 8 minus 2 minus 3 does in fact equal 3. So it goes through the appropriate point. And the thing about our plane that we really want to make sure, if it's properly a tangent plane, it should go through the point, and it should have the same first derivatives. And in fact it does. Hey look, 4, negative 2. So it passes both tests. If you like, you might remember your Taylor series. This is actually a linear, the multivariable equivalent of a first order Taylor expansion. We have done, we are expanding it around this point. And so we've got, kind of the value of our first derivative in here. It turns out that we can do, we can use these tangent planes to do something else. And that something else we call linear approximation. So when we are doing linear approximation, what we can do is we can use this tangent plane in order to approximate the value of a function. Because one of the important things about calculus, one of the fundamental underpinning assumptions of calculus, is that no matter how complicated a curve or a surface is, if I look close enough, if I get small enough to a small enough scale, everything looks linear, everything looks flat. So if I have some function, and here I'm going to kind of go back to BC calculus because it's easier to draw in 1D, that if I have some function like this, and I decide to do a linear approximation around some point, so I draw a tangent line at that point. If I zoom in and enhance, if I get close enough, if I get a little closer, it looks like a pretty good fit. And if I get even closer, enhance, if I zoom in a whole lot, that tangent line gets real darn close to the value of the function. So what we're going to do is we're actually going to say, what if we want to approximate the value of a function using its tangent plane? And you might ask, why would we do this? Why would we not just calculate the function? And it actually is the case sometimes in science that either we know things about the derivatives and we may not know much about the actual function, or it's often the case in like quantum mechanics, this is from my own personal experience, that the original function you're working with is just way too complicated, and so you're going to make it simpler and easier to work with. In this case, we're going to use a modified version of this equation, and we're going to say that the linear is that we're going to approximate a function, so we're going to take some function f of x, y, and we are going to approximate it around some point using this function L. So we're going to approximate it around the point x0, y0. And the way that we're going to approximate it is going to look very much like this. We're going to start at the value f, x0, y0. We're going to add to that fx times x minus x0 plus fy y minus y0. So it's really just this same equation, but we've moved the z0 over to the other side. We've moved z0 over to the other side. So let's do a quick example of that. We're going to approximate this function. We're going to approximate the function x cubed y to the fourth around the point 1, 1. So it's important to note, first of all, that the actual value of the function, 1 cubed times 1 to the fourth is just 1. Let's see, my x derivative is 3x squared y to the fourth, which at 1, 1 is just 3. Fy will be 4x cubed y cubed. So if I plug in 1, 1, I just get 4. So my linearization here of this function looks like the original value of the function plus the x derivative times kind of how far away from 1 we are plus 4 y minus 1. It's worth noting, of course, that if I plug in 1, 1, right, I get 1 plus nothing. So at the point in question, the approximation is perfect, which makes sense. It's a tangent plane. It should actually touch at that one point. And if we use this linearization to approximate, let's say, very close to that, so what's L of 1.1, 0.9? Well, we're going to get 1 plus 3 times, okay, 1.1 minus 1 is 0.1, plus 4 times negative 0.1. And we end up approximating that as 0.9. That is, we've moved a little bit away from the point that we approximated around, and we're suggesting that the value of the function just a little bit away, 0.1 away in x and negative 0.1 away in y, should be about 0.9. And if you actually go ahead and calculate the original function at 1.1, 0.9, you get a true value of 0.873. So it's a reasonably good matchup there.